Okay, question 4. You're given 3 sets of molecules, and we're asked to circle the molecule with the higher boiling point, and then justify your choice. You don't necessarily have to write it in a complete sentence. As you'll see when I give you answers, it's probably just a sort of a short list. But my point is I don't want to read a paragraph of explanation here, and that's not really necessary. So the difference between these first two, only difference is that there's an OH here, and there's not an OH on the right molecule. They both have the same formula, so if you told me that one has a bigger formula than the other, or one has more hydrogens, that's not correct. The only difference is that there's an OH here, and thus we have hydrogen bonding. And of course this is Skill Builder 1.9 and 1.10 if you want to practice this. So remember, we're looking for intermolecular forces. A lot of students just said there's more hydrogens here, there's more carbons. That's not a good answer. You didn't get credit for that. I want a specific intermolecular force that's not present in the other molecule or is more strongly present in whatever molecule you circled. So we should circle this one. It has hydrogen bonding. That's all you have to answer here. That would be full credit for the first set. The next one, there are a few more carbons here, and this is linear, has more surface area, and that equals greater dispersion forces. A lot of students just said there's more carbons over there, so it wins. Well, that's not necessarily true. That's not necessarily true. More surface area, greater dispersion, which is one of the 3 intermolecular forces, is what we want to discuss here. When we have this molecule that's shaped more like a softball, it doesn't have as much surface area. For the third pair, the difference here comes from the fact that there's a dipole moment on the left one. There's no dipole moment on the right one. So has dipole forces. That's all we need here. The left one has dipole forces. It's going to be held more strongly together with other of its fellow molecules. It will have a higher boiling point. No dipole forces in this one means it's going to have a lower boiling point. And these have basically the same molar mass. If you add it up, you probably come up with a 2 gram per mole difference. That's not really enough to make a heck of a difference in the boiling point. So the fact that there's more C's over here is not a good answer. It doesn't matter because one of those extra C's is basically the same mass as an oxygen. So we don't have any more mass or any appreciable difference in the mass. One has dipole forces, the other doesn't. So a lot of students did not remember their intermolecular forces. So it's going to be important that you go back and review Skill Builders 1.9 and 1.10 if you were confused about this question. Number 5. This is the same as Skill Builder 1.7, 1.8. I hope you're catching on that I have placed high importance on these Skill Builder exercises. Hybridization and molecular geometry. So that's not going to be the electronic geometry, that's the molecular geometry. So the hybridization of this nitrogen is sp3. It has a lone pair, and so it's trigonal pyramidal. Remember that this is a carbon along with this. That carbon is sp. It's always linear. This carbon is very simple. It's a CH2. It's sp3 tetrahedral. This oxygen is also sp3. Remember that it has 2 lone pairs, just like in water, so this is a bent molecular shape. This oxygen is sp3 tetrahedral, just like before. This carbon. This carbon here has a hydrogen that we didn't draw. It is sp2. It's part of an alkene, and it is trigonal planar. Those were relatively straightforward. Most students got full credit there. Here again, we're back to resonance structures. So this is Skill Builder 2.8, basically choosing the best resonance structures or choosing the worst one, as it is in this case. So circle which one of the 4 here is insignificant and tell me why. Obviously this one is the best. There are no charges. Or all the rest of them have cations on carbon, so they all have some sort of incomplete octet. So that's not going to be the difference. These 2 here have negative charges on O. This one has a negative charge on carbon. And so that's going to be the difference maker here. This one is the least significant because carbons have opposite charges. There's no reason for carbons to ever really have opposite charges. That's not a proper resonance pattern, right? This arrow does not fit any of the resonance patterns, or the opposite arrow if we want to try to make it go back to the left. So that arrow does not fit any resonance patterns. You should not be drawing that arrow, and thus we should never arrive at this that resonance structure. Okay, so the next one. Here again, this molecule has no charges. That's going to be ideal. All the rest of them have a negative charge on carbon somewhere, so that's not going to really help us make a choice. Then we have a positive on the oxygen, or the carbon, positive on the O, positive on the O. Again, the difference here is that we have two carbons. They happen to be adjacent, but it doesn't necessarily matter, that have opposite charges. There's no reason for that to happen. In order to get that circled image, we need to do this arrow push. It doesn't fit any of the 5 arrow pushes. So that's a good answer for circling the first one in the top, and this is a good answer for circling the second one in the bottom. So really the same answer. For number 7, I honestly can't remember what I was trying to do. I mean, I remember what the type of question I want to ask. I don't know why I wrote it this way. In both of these, if you just count up carbons and hydrogens, you'll find that there are 0 changes. Obviously, there's a change in the structure, but here's an example of something that I was trying to get. So here's question 2.6 is a good example of this type of question. You can review that in the book. But let's look at this potential chemical reaction. And now let's ask us the same question. How many hydrogen atoms are added or lost? And this should be pretty simple to observe. There is a CH3, CH2, CH3. Those are the same as on this molecule. The difference here is that there's an alkene, and there's no alkene. And so we go from CH-CH to CH2-CH2, so 2 H's gained. And indeed, the reagent that I didn't show you, because it's not important, is H2, 2 hydrogens. So the point here is that using these skeletal line structures makes it a lot easier for us to quickly establish what is happening in a chemical reaction. What if we went like this? We could draw this molecule here. Maybe the question is just what happened? All right, we've taken this H and removed it. We've added this CH3. So we've added a carbon and a couple of oxygen or a couple of hydrogens to this reaction. And the skeletal line structure just makes it a lot easier for us to see that. So I didn't really grade this one. If you got it wrong, I just wrote over it in red pen. If you got it right, I just moved on. Sorry if it confused you, but my goal was to have something like this top question or like these questions here. And question 8 was relatively straightforward. Most students had no problem with that. That, of course, is section 2.3, really just memorizing, unfortunately, a number of functional groups. And with repetition, you can become pretty adept at identifying them. Here's an alcohol. This is an ether. And again, we see the utility of the skeletal line structure. Anything that's just a bunch of carbons really isn't a functional group, so we can ignore that part, right? All this stuff we can ignore. It's only the stuff that's pointed to with arrows that our eyes should be drawn to automatically, because it's not just a bunch of lines. So the ester here is this whole thing. This is a ketone. Ketone does not have a Y in it. Lots of students like to put Y's there. And in this arrow, I was trying just to point to this CC double bond. Alkene. If you wrote aromatic, I crossed it off, but I didn't really take off a point for that. But technically, it is an alkene.